There is an exam, midterm, on Monday. I'm going to try and be in my office from around 2 till around 4 at least, if anyone needs to come by. And if there are any questions now about anything related to that, I'll quick questions. Otherwise, we'll start working on trigonometry some more. Do you have a question? No. So I want to pick up on something I left off with on Wednesday, having to do with the right triangle. I have a right triangle, again, there's an opposite side, an adjacent side, and a hypotenuse. And we define some functions in terms of this angle and these sides. We have the sine of theta equal the opposite over the hypotenuse. Cosine of theta is adjacent over the hypotenuse. The tangent of theta is, if you like, the sine over the cosine, or the opposite over the adjacent. So this being a right triangle, we know immediately, we know this angle is theta, we know this angle here has to be 90 minus theta. Because these angles are complementary. Well, that gives us the opportunity to kind of look at these functions in a little different way. You can kind of in your head kind of rotate this triangle over. You really have to do that. Just draw it. I make things simpler. So here's my 90 minus theta degree, my hypotenuse, my adjacent, and my opposite. And now, if I rewrite these functions in terms of this, I'm going to see that my sine of 90 minus theta is going to be what? It's going to be the opposite, but that's the A side. It's going to be A over H. The cosine, 90 minus theta, well, that's going to be this adjacent side, which we're calling O, over the hypotenuse. And the tangent, that's going to be what? It's going to be the opposite over the adjacent. That's A over O. So we can see kind of a correspondence between these. And I'm going to use the word identity. I'll explain what I mean by that in a second. But we can see that the sine of 90 minus theta is A over H. That's just cosine of theta. Cosine of 90 minus theta, similarly, we can see O over H is the sine of theta. And the tangent of 90 minus theta, well, let's see, over A over O, that's 1 over the tangent of theta. So what I mean by an identity is a statement. It doesn't have to involve trig functions. We're going to see it mostly in the context of trig functions, which is true for all theta. So we have these 3 identities now that we can use when we need to. One nice thing about this is if we were, cast off on some desert island and we have a book of trig functions, but unfortunately the second half of it is, worn away. We can't read it. If we merely have the trig functions for theta between 45 degrees and 0 degrees, that's sufficient. So if we wanted to find the, let's say we wanted to find the sine of 70 degrees, well, that's equal to the cosine of 90 minus 70, or cosine of 20 degrees. So we really only need these values between 0 and 45 to really have the whole table. But there are lots of other uses for these identities. Later in the course, we're going to spend some time looking at various trig identities and showing how you might prove that something's an identity. Okay. I'm going to try something a little different now. Just put these aside in your mind for the moment. This didn't work out just the way I hoped in the last class, but they were really sleepy. Maybe you guys can be a little less sleepy. I want to kind of outline dealing with a certain set of problems. I want to kind of map it out. And I know not everyone here is a computer programmer. I don't want to overemphasize this connection. This is kind of the way a computer programmer might go about thinking about a problem. But it's also useful. It's just a very logical way to break down a problem and kind of get the whole scope of it. So the problem I want to deal with is what I'm going to call solving a right triangle. Right triangle. Right triangle has one right angle. And what I mean by solving it is, given sufficient information about this triangle, I want to find everything about it. So, for example, let's just start with, let's say I just know one of the sides here. I'm going to call this L1 because it's a leg, and there are two legs. Well, by definition, I know that I have one angle. I always know one angle, right angle, and I have a leg. And I want to solve this, and I look at it and I think, well, that's not really sufficient. I could have a different triangle with the same length. It's a right triangle. But the hypotenuse is a different length. The other leg is a different length. The angle is something different. So this is not sufficient. So the first question is, what is sufficient? Now, as a general rule, you need 3 components of a triangle to solve it. So we start off automatically with 1. We want to be a little careful, though. If, let's say we know, I'm going to call the angles here alpha and beta. If I know alpha and beta and the right angle, this is one example where I know 3 components, but it's not sufficient. Anybody know why it's not sufficient to determine this triangle? Scratch my head a little. I know most of my students I've found are very weak on their geometry. I think that's because some of them took it as freshmen in high school. It's like, how many lifetimes ago was that? There's a theorem in geometry, triangle theorem, called the AAA theorem, angle, angle, angle. But it's not a congruence theorem. It doesn't describe 2 triangles being congruent. Instead, it describes 2 triangles being something else. Anyone remember what else these triangles could be? Yes?
Similar?
Similar. Yes, thank you. Similar. Spelling's failing today. Similar triangles. Similar triangle, 2 similar triangles. They have the same angles, alpha, beta, gamma. These are Greek letters. They're nice, easy ones. They sound like A, B, C, right? But we're going to use them. Beta, gamma. Let's call the sides to this triangle A, B, and C, and we'll call these capital A, capital B, capital C. With similar triangles, I do know a little bit. I know these sides don't have to be the same, but I do know that they are in proportion. So by that I mean little a over little b. This ratio is the same as big A over big B, same B and C and A and C. So that's useful information, but it kind of doesn't apply for today. The important thing to realize is that just knowing alpha and beta, that doesn't really allow me to solve this triangle. Incidentally, I don't really need to know alpha and beta to know this is a similar triangle. To know 2 triangles like this are similar. I have 2 right triangles, and they both have one of the angles. Of course, one of the angles is a right angle, but they could have the same alpha. I know all 3 angles are the same because their sum has to be 180, right? All right, so that we've eliminated that. So let's look at what the possibilities are here. So I've got my 2 legs, my alpha and my beta. So let's say let's start off with I know alpha, I know beta. And a leg and a hypotenuse. Okay, so here's 3 things that should determine a right triangle. I could know beta, L1 and H. I could know alpha L2 in H, beta L2 in H. I could know alpha L1 and L2. I could know beta L1 and L2. In all of these, of course, no. Wait a minute. I'm doing this for my head without my notes. It makes it rather serious here. Let me start over. In all cases, I have a right angle that I know, right? So that's one. So I might know alpha and L1. I might know beta and L1. I might know alpha and L2. I might know alpha L1 and L2. Beta and L2. I might know alpha and the hypotenuse. I might know beta and the hypotenuse. Okay. That's 6 cases here. 1, 2, 3, 4, 5, 6. Those are the cases where I know an angle. The other possibility is I know 2 sides. So, for example, I might know L1 and the hypotenuse. I might know L2 and the hypotenuse. I might know L1 and L2. Okay, those are 9 cases that I might have to deal with, but I want some kind of algorithmic map here for how to solve each one of these. That's my goal. So the first thing I want to do is I want to simplify this somehow. I want to kind of coalesce problems that are really the same problem, or can be made to be the same problem. So the first thing I'm going to do is I'm going to say, look, 1 and 2 really aren't all that different. In one case I know alpha, in the other I know beta. But if I know alpha, I can find beta, right? That's just 90 minus alpha. So really, these two, I can combine them using, I'll call it the Hague process, but what I mean is the triangle has 360 degrees. So let's call this 1, 2 now. And similarly here, I can use this. This is 3, 4. And these two are the same. 5, 6. All right, so now I've taken six cases, and now I've made 3 out of them. That's good. Here I have 3 cases that I actually can combine. There's a process I can use. Let me see if I can get you guys to kind of think this through a little bit. I have a right triangle and I have 2 sides. In each case, I want to find the 3rd side. What am I going to use? What can I use to find that 3rd side? Yes?
The Pythagorean theorem.
Pythagorean theorem. Right? See, now I have in all 3 cases L1, L2, and the hypotenuse. So I'm just going to call this 7, 8, 9. All right. So now I've taken 9 cases, and I really only have 4 left to deal with. I'm wondering if I can do a little better. well, wait a minute here. Here I know L1, L2, and I use this to find alpha and beta, right? Here I know, oh, wait a minute, hold on. Take that back. Okay. L1, L2, alpha and beta. L1, alpha and beta, L2, alpha and beta. There's a symmetry there. You see that? If I just relabel this, I just label alpha here and beta here, you can see that these two are really the same. It's the same problem. Just think about that for a second. I just take this see if I can write that a little better. In this case I'm talking about, I know alpha, I know beta. In one case I know L1, I have my right angle. If I flip this, right, what does that look like? It's now alpha, beta, L1. But that looks the same as alpha, beta, L2, right? I've just kind of relabeled it. So these are really the same problem. This is really 1, 2, 3, 4. I only have to solve it once. Okay, so now, you know, none of this really has to do with trigonometry yet. I haven't had to use any of my functions yet, but I've got it down to where now 9 cases are now just 3 different problems to solve. All right, I want to go ahead and actually try to do something with this now. I guess I still need my diagram. Beta, L1. Okay, let's go at this one for a second. So I have a leg, and I have 2 angles, and I want to find some other component. How can I do that? Right. Remember, what do I have at my disposal? Sine of theta is the opposite over the hypotenuse. Cosine of theta is the adjacent over the hypotenuse, and my tangent. How can I use one of those? Find a component that's missing. Obviously, there's some dead air here. That's okay. You know, some of you were thinking, what is he asking? And you think, if I only knew what he was asking, I could answer. That's really true. That's what this is really about. What am I asking here? I have a triangle. I could give you a specific example. Let's say I said, I have a triangle, this is 33 degrees, and I have a right angle, and I know this is 5. Okay? I want to figure out the other components of this triangle. I have enough information. I have 2 angles and an included side. I know that's sufficient, especially with a right triangle. What do I need to do to find one of the other components? Well, okay, let's fill this in. We know that this is 57 degrees, right? We have 3 angles. How can I find one of the other sides? Whisper to me, I will not hear. Yes? Plug it into what? Which formula? Oh. No, it's the one you want to use. Well, pick one. Just pick one randomly. All these. 1, 2, and 3. Which one?
2.
2. Okay, let's try that. The cosine, well, let's do it here with 33 degrees first, equals what? The adjacent 5 hypotenuse. Oh, there's just one unknown. The hypotenuse equals 5 over cosine of 33 degrees. Okay. All right, now I've got my hands dirty. I think, let's go back to what I'm asking here. I know either L1 or L2. So I say that cosine of alpha equals L1 over H. But I know L1, just don't know H. So H is L1 over the cosine of alpha. All right. So I'm going to call this process C because I use the cosine. So now I know the hypotenuse, right? I know alpha and beta. I either know L1 or L2, and now I have the hypotenuse. Okay. I'm not quite done, right? I've got 3 angles and 2 sides. I want to find that 3rd side. How can I find that 3rd side? Hint. There's at least 3 different ways to do it. How do I find L2? Yes? Oh yeah, the Pythagorean theorem. Yeah, okay, that's good. Okay. So now I have all 3, right? Okay. This is so hard. We're solving all the right triangles now and forever. So I know it's hard. Okay, let's go back over here. Here we have alpha or beta, which means we have alpha and beta, and we have the hypotenuse, right? That's 5 and 6. So I have alpha and beta in the right angle, of course, we always have that. And I have the hypotenuse, and I want to find L1 or L2. How do I do that? And before you say anything, I'm going to say, plug into the formula, okay, right? Which formula? Give me a formula. Not you. You know the answer. Somebody else. You know, I know, you know, like steam is coming out of people's ears. Well, people have something between the ears, but steam is coming out of the ears, and it's like you're used to like going into a class and you know, they give you a specific problem and say, well, okay, the hypotenuse is 10, and the angle is 40 degrees. What are the other sides? But here I'm not asking that. I'm not asking a specific problem. I'm trying to get it in general. How do we do this? And lots of times when we're trying to solve a problem in the real world, it's not, for us, especially in math or in computer science, we're not trying to solve it for specific data. We're trying to solve it for whatever data comes along. Right? That's what this is. The input data is I'm giving you 3 starting points, and we need to know the path to the answer for all of them. All right, so what formula am I going to use? guess. Yeah, pick a number between 1 and 3.
2.
2. We already used that. All right, let's try it. See. Cosine of, what do we know here? We know alpha. We know beta too, but we'll say alpha. So the cosine of alpha is what? That's L1 over H. And what do we know? We just know H. But we know alpha, right? So we can use a little algebra, and we can say H equals L1 cosine of theta. No, I'm sorry. We know H. We know cosine of theta. We don't know L1, right? L1 equals H cosine of alpha. Okay. Call that the seed process again, since we used the cosine again. All right, so now we have L1, H, 3 angles. We're almost done. How else can we find? How can we find the last? What are we missing? L2. How can we find L2? Speak up so the class can hear you, and your deaf professor. I can't hear you.
Tangent.
Tangent. Oh, okay, we can use a tangent? Okay, let's see. A tangent of which angle? Alpha? Sounds good. Tangent of alpha equals what? Opposite L2 over the adjacent. Oh, yeah, we found L1, right? We just don't know L2. L2 is L1 tangent of alpha. Okay. So we could use call it the tangent. We also could have used P, couldn't we? The Pythagorean, right? Because we had a hypotenuse in L1. We could use that. And if you think a little bit, you could probably use the sine or the cosine too. Like once you get to the last item, there's a few different ways to do it. And you know, if we actually do a real problem, you may have to think which do you prefer. Prefer the Pythagorean theorem, and something else with a sine or cosine. Okay, we're almost done. We've got 1, 2, 3, 4, 5, 6, all done. Now we just have to look at 7, 8, and 9. 7, 8, and 9, we have 3 sides and 1 angle. We have a right angle. How are we going to solve this? Yes?
We can use the formulas and then the inverse sign.
Okay. Formula 1.
Well, for instance, yeah, and then rearrange so that the angle is...
Okay, let's try that. So sine of alpha, we don't know alpha, right, is what? It's L2 over H. We know these two, and you said use the...
Inverse sign.
Okay, everyone, listen up. Remember inverse functions. We're going to have inverse functions for sines and cosines. And you know that because there's a button on your calculator, right? It's the inverse. So let's find the inverse sine of both sides. Okay, so what is the inverse sine of the sine of alpha?
Alpha.
Not you. Alpha. No offense, I just, you know, everybody else to wake up. Yeah. Okay, so we'll call that the inverse sine process. Okay, what did that do? That gave us alpha. Okay, we're not done. We still need, yes? Why are we using inverse? Okay. I like your question. I do. It's a good, you know, because, I mean, I don't know, but I think somebody in this class is asleep. Their eyes are open, but they're asleep. Your eyes are open, right? You're asking a good question. So let's look at this. We know H, L1, and L2. Let's use each one of these, right, to see what we can find out. We have the right angles too, that's correct, yes. That's why we can use the Pythagorean theorem, and that's why we can use these definitions. Because right now, that's how these definitions are defined in terms of a right triangle. So we could say the sine, let's say the sine of alpha is, what did we decide? That's L2 over H. Cosine of alpha is, that's L1 over H. Tangent of alpha is L2 over L1. Okay. And again, these are the things we know, right? This is the question mark. We could just as well use the cosine. I'm sorry, we could just as well use beta. You know, sine of beta is equal to, now it's L1 over H. Cosine of beta equals L2 over H. And tangent of beta, we know beta, right? Do we know beta? No, we don't know beta, right? Don't know beta. So the tangent of beta is that's L1 over L2. Okay, so again, we know all of these, we don't know beta. I think we need to use an inverse function one way or another. We really have our choice, inverse sine, inverse cosine, inverse tangent. Think about it. We know three sides, and we know it's a right triangle. We need to get an angle. We don't have a function, you know, non-inverse function. It gives us an angle. Inverse function that gives us an angle. Does that help? Yeah. Okay, you got to think all around this to really understand the problem. Okay, so we did the inverse sine. How do we find the last angle? I don't want to use C because we already used that for cosine. CO, complementary angle, right? Once we know one angle, we know the other one. But we could use other methods too. We could use the inverse cosine and find the other angle. Okay, what is this thing? Now we're done. This is a map. We've got problems. We have input is our problem where we get three pieces of information. We have to break it up into the categories and we coalesce some of them. We use some information, Pythagorean theorem, definitions of sine and cosine, and our ability to exercise those functions, at least right now, just on a calculator. So if you were a computer programmer, now you can go ahead and you know, oh, I need some code here and here and here. Maybe I need some code here to differentiate what I've got. Or maybe I make the user type the stuff in some way. All right. We're going to come back to this idea later in the class. I thought this would be a simple problem because it's a right triangle. But we're going to come back to a more complicated problem later. We're going to just look at a general triangle, right? Alpha, beta, gamma, A, B, C. And we're going to look at the same problem. Because I give you three components, not three angles, because that would just be a similar triangle. And how do we solve this triangle? How do we find all its constituent parts? We do not have the knowledge to do that yet. We do not have the equipment. We're going to develop that a little later. Question? Next thing we're going to look at, we're going to look at angle measurement in a little detail. You recall from geometry, we define an angle. Well, it's a little ambiguous, but we talk about two rays with a common vertex, and we talk about them creating an angle. Sometimes we talk about the measure of an angle. Measure of an angle, it's like a little like distance, but it's not the same as distance. We talk about the measure going completely around in a circle as a terrible circle. I don't think I'm going to need this. That's a little better. What's the distance completely around this circle? 360. 360 degrees. Not temperature degrees, angular degrees. We talked about this before, but 360, that seems like an odd number. I mean, we're so used to it that, it may not seem odd. But this goes back to the Phoenicians, who had a base 60 number system. They didn't have zeros, and they didn't have, the idea that this is the tens and this is the ones. They just had symbols. And base 60 has an interesting feature that is likable, although not as nice as what we use. 60 is divisible by 2, 3, 4, 5. It's not divisible by, it's divisible by 6. It's not divisible by 7. It's not divisible by 8. But it is divisible by 10, which is nice. And then 12, 15, and 30. So that's just a nice feature of it. We run into this number in other things that seem odd that they go back that far, such as the number of minutes in an hour, or the number of seconds in a minute. I kind of wonder why we don't have 36 hours in a day. I bet there's a good explanation for that. But, okay, so thing is, this is just an arbitrary. Someone will have to keep track of time for me. This is just an arbitrary kind of number, an arbitrary scale. It's actually not the only scale we use for angular measure. There's another scale called a grad. 400 grad degrees in a circle. A little different. I think someone was thinking of decimal because a right angle is 100 grad, 100 degrees of grad. I think it's used in navigation under some circumstances, but it's unlikely you'll run into it. But there is another scale that we use called radians. No doubt have run into this word before because on your calculator in the mode, see there's degrees and radians. You might think, why would I ever want to switch from degrees? Well, I will have a reason to. We define radians a little oddly. We take an angle and we draw a unit circle at the vertex. So the circle has a radius of 1. And then we look, I'm going to call this little s, the distance here of this arc. And we define the radian measure, we use theta here, as that length s. There's an alternative way you can look at it, which works just as well. Instead of taking a unit circle, you just take some arbitrary circle of radius r. And now we'll call this distance here large S. And then theta just equals the capital S over the radius. These two are both the same because these circles are similar. The ratio of their parts is the same. And S here and S over R are the same ratio. It's S over 1. Okay, let's talk about radian measure for a minute. I said it's, did I say this in this class? It's kind of a more natural scale for angles. It doesn't seem that way because, as you're going to see in a second, a very strange number is going to pop up in radian measure pi. Let's look at that. So if I have degrees over here, and I have a whole circle that's 360 degrees, well, if I have a unit circle, radius 1, what's the distance around the circle? No. Diameter is now going to be 2. Right? So what's the relationship between the circumference and the diameter of a circle? What's that relationship? know the phone number of the morgue? People are dead here. What's the ratio of a diameter to the circumference?
5 times the diameter.
Times the diameter. Okay. So the circumference is 2 pi times the radius, right? So if I divide the whole distance around C by R, that's my theta, right? It's 2 pi radians. Okay. Because we're going to work with radians, there's a few particular radian measures that are so special that you really need to be familiar with them, just the way you're familiar with 360 degrees. So, for example, if I had 180 degrees, that's kind of strange, but it's called a straight angle. It's kind of like a line. Your rays just branch out and go in opposite directions. How many radians would that be? 5, right? Another important angle is our perpendicular angle, our right angle, 90 degrees. That has to be what? Pi over 2. Right. Another very important angle, the angle in an equilateral triangle, or a 30, 60, 90 triangle. 60 degrees. Somebody else wake up, please. Thank you. Pi over 3. Okay. We know 60, we should know 30. That's 5 over 6. And one more important angle you really should be familiar with, 45 degrees, is going to be right here, pi over 4. Okay, I mean, another way of looking at this is, what's the conversion factor? Right? If I have degrees and I want to multiply it by something and get radians, well, if you remember this table, you could use either of these. You could say it's 2 pi over 360 degrees, or some people prefer pi over 180 degrees. And you can reverse this, of course. Radians times 360 over pi is degrees, or 180, 2 pi, or radians times 180 over pi is degrees. Okay. We're gonna do one more thing. We're gonna make some use of this in a particular application. Anyone who doesn't know the answer to the next question, please come to office hours. Please. What is the area of a circle with, I catch your interest, radius r? Area equals what? Everybody's going to come to. Somebody, yes?
Pi r squared.
Pi r squared. So if you didn't know that, please come get help. Okay, so if I have a circle, I want to know the area of it, I can figure it out if I know the radius. On the other hand, what if I wanted to know the area of a whole circle, but what we call a sector of the circle. I know the radius, and I know this angle. And in particular, I know this angle in radian measure. Well, there's going to be a relationship here, right? The area of this sector is going to be to the area of the whole circle. As my area, my little theta sector, is going to be the area of the whole circle. As the ratio of theta is to the radian measure of the whole circle, which is pi. Okay, this is what I want to know. So the area of my sector is going to be area of my circle times theta over 2 pi. But what's the area of my circle? That's pi r squared. So pi r squared theta over 2 pi. The pi's are going to drop out, and I'm just going to get r squared theta over 2. So that's the area of the sector here of angular measure in radians times and the radius r. Let's just do one example and call it a day here. I have a sector. My circle has radius 3 meters, and my angle is 45 degrees. 45 degrees. Well, 45 degrees is what? In radians. Pi over 4, right? So my formula says it's going to be r squared times theta over 2 is what? 9 pi over 8. That's the area of my sector. Okay. Good luck. Don't worry too much about trig this weekend. Study hard, but not too hard. Have a little fun to relax. Come in and